In the deepest reaches of space, where the rules of reality itself begin to unravel, there exists something so massive, so impossibly dense, that it defies comprehension. A cosmic monster that makes our sun look like a grain of sand on an endless beach. A gravitational predator so powerful that it could devour entire solar systems in mere moments. This is not science fiction. This is not speculation. This is the story of Phoenix A, one of the most extreme objects ever discovered in our universe. A black hole so massive that scientists struggled to believe it could even exist. When we look up at the night sky, we see stars, thousands of them on a clear, dark night. Each one of those points of light is a sun, many of them larger and more massive than our own. Some are small red dwarfs that will burn for trillions of years. Others are blue giants that live fast and die young in spectacular supernova explosions. The variety is staggering, yet all of them share something in common. They are stars, balls of hydrogen and helium undergoing nuclear fusion, converting matter into energy through the same basic process that powers our sun. We understand them, we can measure them. We can predict their life cycles with remarkable accuracy. But Phoenix A is nothing like a star. It is something far more extreme, far more alien, far more challenging to our understanding of physics and reality. It exists at the boundary of what our theories predict is possible, in a realm where the fabric of space and time itself becomes twisted beyond recognition. To even begin to comprehend what Phoenix A is, we must first understand the immense scale we're dealing with. And that requires understanding just how massive our own sun truly is. To understand just how extraordinary this object truly is, we must first grasp the scale of what we're dealing with. Our sun, the star that gives life to Earth, that lights our days and warms our world, weighs approximately 200,000 trillion pounds. That's a 2 followed by 30 zeros. It's a number so large that our human minds can barely process it. The Sun contains 99.8% of all the mass in our entire solar system. Jupiter, Saturn, all the planets, all the asteroids, all the comets combined make up less than 1/5 of 1% of what remains. Every second, the Sun converts about 4 million tons of matter into pure energy through nuclear fusion. Despite this prodigious consumption, the Sun has burned through less than half of its hydrogen fuel and has billions of years of life remaining. The Sun's gravity holds 8 planets and countless smaller objects in orbit, its influence extending halfway to the nearest star. Now, imagine taking that Sun, that colossal ball of burning plasma, and multiplying its mass by 10 billion. Not 10 million, not 10,000, but 10 billion suns compressed into a single point in space. This is Phoenix A. Based on the most recent analysis using NASA's James Webb Space Telescope, combined with Chandra X-ray Observatory data from 2025, Phoenix A harbors a supermassive black hole containing approximately 10 billion solar masses, making it one of the most massive black holes ever confirmed through multiple independent measurements. If you placed it where our Sun is, its event horizon, the point of no return, would extend roughly 40 times farther from the center than Earth orbits the Sun, reaching well beyond the orbit of Mars and into the asteroid belt. The entire inner solar system would be contained within this monster's gravitational prison. Let's truly comprehend what 10 billion solar masses means in practical terms. If you could gather 10 billion stars identical to our Sun and compress them all into a single point, you would create Phoenix A. The Milky Way galaxy contains between 200 and 400 billion stars. Phoenix A contains roughly 2.5 to 5% of all the stellar mass in our entire galaxy, compressed into a region just a few light days across. The event horizon of Phoenix A has a diameter of approximately 59 billion miles, or roughly 95 billion kilometers. To cross from one side to the other at light speed would take about 88 hours, nearly 4 days. For comparison, light takes only 8 minutes to travel from the Sun to Earth and about 5.5 hours to reach Pluto. The sheer scale becomes even more apparent when you consider that Neptune, the outermost planet in our solar system, orbits at about 2.8 billion miles from the Sun. Phoenix A's event horizon is more than 20 times larger than Neptune's entire orbit. What makes Phoenix A particularly remarkable is the combination of this mass with its exceptional activity level. Many supermassive black holes of similar mass exist in a quiescent state, barely accreting matter. Phoenix A, by contrast, is actively feeding and launching the most powerful jets ever conclusively observed from a supermassive black hole. These jets extend for approximately 7.5 million light-years from end to end, making them 75 times longer than the diameter of our entire Milky Way galaxy. If Phoenix A suddenly replaced our Sun, the consequences would be immediate and apocalyptic. Earth's orbit would change instantly as the gravitational field increased by a factor of 10 billion. We would either be pulled toward the event horizon or flung into interstellar space. Either way, life on Earth would end within seconds as gravitational forces triggered catastrophic earthquakes, volcanic eruptions, and complete atmospheric disruption. The sky would darken as we fell toward oblivion, or brightened impossibly as we were ejected into the void. The tidal forces from Phoenix A would be extraordinary even at great distances. Any planet venturing within a few astronomical units would experience forces capable of geological transformation, sufficient to melt rocky planets entirely into molten spheres of lava. Gas giants would be stripped of their atmospheres, their outer layers torn away and added to the accretion disk. Even at distances where Earth currently orbits, the differential gravitational pull between the near and far sides of our planet would create forces millions of times stronger than those that cause our ocean tides, literally tearing our world apart. The accretion disk around Phoenix A glows with the combined light of millions of galaxies worth of stars, yet all this emission comes from a region smaller than the orbit of Mars. This is what we observe when we look at Phoenix A, the death throes of matter compressed, heated, and accelerated to unimaginable extremes before crossing the point of no return. But Phoenix A doesn't just dominate space through its mass and luminosity, it dominates time itself. Einstein's general relativity tells us that gravity affects the flow of time. The stronger the gravitational field, the slower time passes relative to regions with weaker gravity. Near Phoenix A, these time dilation effects become extreme. A clock just outside the event horizon would tick extraordinarily slowly compared to one far away in deep space. What seems like 1 hour near the horizon might be several days or weeks for someone watching from a safe distance. This is the literal prediction of Einstein's equations, confirmed by countless experiments and observable in GPS satellites orbiting Earth, though on a far smaller scale. But raw numbers, as staggering as they are, don't tell the full story. To truly understand Phoenix A, we need to journey back to its discovery, to understand what it is, how it formed, and what its existence tells us about the universe itself. This is a story that spans billions of years, crosses incomprehensible distances, and challenges everything we thought we knew about the limits of cosmic scale. It's a story that begins not with the black hole itself, but with the strange, brilliant objects that led us to discover it. It's a story of human curiosity, persistence, and the gradual unraveling of one of the cosmos's deepest mysteries. Long before we understood what they were, astronomers observed strange point-like sources of light in the sky that appeared to be stars but behaved in ways no star ever could. These objects, first catalogued in the 1950s and 60s, emitted tremendous amounts of energy, far more than entire galaxies containing hundreds of billions of stars. Yet they appeared as tiny points of light, no larger than a single star when viewed through even the most powerful telescopes of the era. Their appearance was stellar, star-like, but their nature was anything but ordinary. In 1960, astronomers made a breakthrough using the Palomar Observatory's 200-inch telescope. They identified the optical counterpart of a strong radio source called 3C48. It looked like a faint blue star, but its spectrum was completely unprecedented. The emission lines were shifted dramatically toward the red, suggesting either enormous velocity or tremendous distance. If this object was billions of light-years away and yet still detectable from Earth, it must be emitting an absolutely staggering amount of energy, far exceeding anything previously known. The name given to these mysterious objects reflected this confusion. They were called quasi-stellar radio sources, quickly shortened to quasars. As telescopes improved, astronomers discovered that quasars were spectacularly bright, able to outshine an entire galaxy of 200 billion stars by a factor of 100 or more. The brightest quasars were visible across the entire observable universe, their light traveling for billions of years before reaching our telescopes. Throughout the 1960s, astronomers catalogued hundreds of quasars. All shared certain characteristics: tremendous luminosity, compact size, and dramatic variability. Quasars could brighten or dim over days to months, which told astronomers something crucial. An object cannot vary in brightness faster than light can cross it. This constraint suggested that quasars were concentrated in regions no larger than our solar system. How could something so small produce so much energy? The physics seemed impossible. Even more puzzling was their distribution. Quasars appeared predominantly at enormous distances, billions of light-years away. Astronomers were observing them as they existed billions of years in the past, looking back in time through the light travel delay. The most distant quasars were seen when the universe was less than 1/10 its current age, in an epoch when the cosmos was younger, hotter, and far more chaotic. Quasars were clearly relics from a more violent era. But what could possibly generate such incredible energy? For years, astronomers proposed various explanations. Perhaps massive stellar collisions, thousands or millions of stars crashing together in dense galactic cores. Perhaps huge explosions, similar to supernovae but unimaginably larger, powered by unknown physics. Perhaps entirely new physical laws operating in the extreme conditions of the early universe. Theory after theory was proposed and found wanting. None could adequately explain the observations without invoking exotic physics or violating known laws? The answer, when it finally emerged, was both elegant and terrifying. Quasars were supermassive black holes actively feeding on vast quantities of matter. The brilliant light came not from the black holes themselves, which emit no light, but from the superhot accretion disk surrounding them, a swirling maelstrom of doomed matter spiraling toward oblivion. The energy source was gravitational, the most fundamental force in the universe, operating at its most extreme. The key insight came from understanding energy conversion efficiency. When matter falls into a black hole, it releases gravitational potential energy. Matter falling from a large distance to just outside the event horizon converts about 10 to 40% of its rest mass energy into radiation, depending on the black hole's spin. This is calculated using Einstein's equation: energy equals mass times the speed of light squared. The faster the black hole spins, the closer matter can orbit before plunging in, and the more energy can be extracted. To understand how efficient this is, compare it to other energy sources. Chemical reactions like burning coal or gasoline convert less than 1/1,000,000th of mass into energy. Nuclear fission, used in power plants and atomic bombs, converts about 0.1%. Nuclear fusion, powering stars including our Sun, converts about 0.7%. But black hole accretion converts 10 to 40%, making it by far the most efficient continuous energy production mechanism in the known universe. Nothing else comes close. This incredible efficiency means that a black hole consuming just a few solar masses of material per year can power a quasar shining brighter than 100 billion stars. For phoenixa, with an estimated luminosity exceeding 10 to the 40 watts, the accretion rate is approximately 5 to 10 solar masses per year. That may sound modest for such a massive black hole, but it represents an enormous energy output sustained over millions of years. This realization transformed our understanding of both quasars and black holes. Black holes, once considered exotic theoretical curiosities that might not even exist in nature, were not just real, but central players in the story of cosmic evolution. Every large galaxy appeared to harbor a supermassive black hole at its center. Our own Milky Way has one, Sagittarius A star, containing about 4 million solar masses. The nearby Andromeda galaxy has one roughly 40 million solar masses. And in the early universe, when quasars were common, these black holes were actively feeding and shining as brilliant beacons across cosmic space. And the brightest, most energetic objects in the universe were being powered by the most extreme gravitational fields nature could produce. Quasars were black holes caught in the act of feeding, their enormous appetites betrayed by the brilliant death screams of matter falling to its doom. As the 1970s progressed and this picture solidified, astronomers realized they had discovered a new window into the universe's history. By studying quasars at different distances, looking back to different epochs in cosmic time, they could trace how galaxies and black holes evolved over billions of years. They could watch the universe change from a violent, chaotic youth filled with brilliant quasars to the calmer, more sedate cosmos we see today. The understanding that quasars were powered by supermassive black holes raised new questions, even as it answered old ones. How did black holes grow so massive? How did they form in the first place? What determined which galaxies hosted bright quasars and which didn't? Why were quasars common in the early universe but rare today? These questions would drive decades of research and observation, leading eventually to the discovery of extraordinary objects like Phoenix A. Phoenix A was discovered in the constellation Phoenix, a faint pattern of stars visible from the southern hemisphere. The constellation itself was named by 16th century explorers who mapped the southern skies for the first time, naming it after the mythological bird that rises from its own ashes. How fitting that this constellation would lend its name to one of the most extreme objects ever discovered, a black hole so massive it challenges our understanding of how such monsters can be born. The discovery of Phoenix A didn't happen overnight. Like most major astronomical discoveries, it was the result of decades of patient observation, careful measurement, and gradual realization. The object was first catalogued as a radio source in the mid-20th century during systematic radio surveys of the sky. Early radio astronomers, using relatively primitive equipment by today's standards, detected powerful radio emission coming from this region of space. But they had no idea what was producing it. The radio waves were strong, but the source appeared extremely distant, and optical telescopes of the era could barely detect anything at that location. As radio astronomy advanced through the 1970s and 80s, astronomers developed more sophisticated techniques for pinpointing the exact locations of radio sources and studying their properties in detail. They discovered that the radio emission from the region of Phoenix A wasn't coming from a single point, but from an enormous structure. Two giant lobes of radio-emitting plasma extended on either side of a central bright spot, stretching across millions of light-years of space. This was the telltale signature of a radio galaxy, a type of active galaxy where a supermassive black hole launches powerful jets that pump energy into the surrounding space. Radio galaxies had been studied since the 1950s. But Phoenix A stood out immediately as extraordinary. The radio lobes were among the largest ever observed, and the power required to inflate such enormous structures was staggering. Something truly monstrous had to be lurking at the center. Through the 1990s and 2000s, as optical and infrared telescopes improved, astronomers were finally able to study the galaxy at the heart of this radio structure. What they found was a massive elliptical galaxy, one of the largest known, sitting exactly at the center of the radio emission. This galaxy, now called Phoenix A, or sometimes Phoenix Cluster Central Galaxy, was clearly the host of whatever was producing the spectacular radio lobes. The breakthrough in understanding the central black hole came from detailed spectroscopic observations combined with modern space telescopes. Spectroscopy breaks light down into component wavelengths, creating a spectrum that acts like a fingerprint revealing composition, temperature, density, and motion. Every element has a unique pattern of wavelengths at which it emits or absorbs light. When a source is moving, all wavelengths shift due to the Doppler effect, just as a siren changes pitch as an ambulance passes. In Phoenix A, astronomers looked at emission lines from hot ionized gas in the accretion disk and the surrounding region. This gas, heated to millions of degrees by the intense radiation and magnetic fields, emits characteristic patterns of light. But near the black hole, gas moves at extraordinary speeds, thousands or tens of thousands of miles per second. When we observe all this gas simultaneously, the emission lines appear broad and smeared out, spread over a range of wavelengths. The degree of broadening directly measures the velocity range of the gas. For Phoenix A, the emission lines were extraordinarily broad, corresponding to velocity differences exceeding 15,000 miles per second. When astronomers plugged these velocities into their equations, the calculated mass was stunning. Initial estimates in 2012 using Chandra X-ray observatory data came in around 20 billion solar masses, making it one of the most massive black holes known. However, more recent analysis in 2025 using NASA's James Webb Space Telescope, which can peer through dust and observe in infrared wavelengths invisible to earlier telescopes, refined this estimate to approximately 10 billion solar masses. This revision came from better measurements of the velocity dispersion of stars in the galaxy's central region and improved modeling of how gas moves in the extreme gravitational field near such massive black holes. This was still controversial initially. Black holes this massive were thought to be extraordinarily rare, perhaps numbering only a few dozen in the entire observable universe. Skepticism was healthy in science. Astronomers examined every possible source of error. Could there be multiple black holes orbiting each other? Could the emission be contaminated by gas moving for other reasons? Each possibility was investigated through additional observations. Different telescopes were used, targeting different spectral lines and different wavelengths of light. Each independent measurement converged on similar values. The emission lines really were as broad as they appeared, the stellar velocities matched, and the mass really was approximately 10 billion solar masses. Further confirmation came from studying the luminosity of the central region. A black hole accreting matter at a given rate produces a characteristic luminosity that depends on its mass and the efficiency of energy conversion. For phoenixa, the observed luminosity was consistent with a 10 billion solar mass black hole feeding at a moderate to high rate. If the black hole were significantly less massive, say 2 billion solar masses, it would need to be accreting at an impossibly high rate to produce the observed luminosity, likely exceeding theoretical limits known as the Eddington limit. If it were significantly more massive, say 30 billion solar masses, the accretion rate would need to be implausibly low given the availability of gas in the surrounding cluster and the evidence of ongoing star formation. The mass of 10 billion solar masses fit all the observations consistently across multiple independent methods. Yet another line of evidence came from studying the jets themselves. The power required to launch and sustain jets extending 7.5 million light-years and inflating such enormous radio lobes could be calculated from observations of the radio emission. This power output, in turn, could be related back to the mass of the black hole through models of jet formation and energy extraction. Again, the numbers pointed to a black hole mass in the range of 10 billion solar masses. A less massive black hole simply couldn't produce jets this powerful without unrealistic assumptions about energy extraction efficiency approaching 100%, which would violate fundamental physics. As evidence accumulated through the late 2000s, early 2010s, and now with 2025 refinements from JWST, the scientific community has firmly accepted the reality of phoenixa. This black hole is real. It contains approximately 10 billion solar masses, making it roughly 2,400 times more massive than Sagittarius A star at the center of our Milky Way, and it represents something at the absolute extreme of what the universe can produce. The discovery raised profound questions. How did such a monster form? What chain of events over billions of years led to the creation of an object this massive? And are there even more massive black holes waiting to be discovered in the most distant reaches of space? In our daily lives, space seems perfectly flat and unchanging. We move through it freely in any direction. Time flows steadily from past to future at an apparently constant rate. Gravity appears to be a force that pulls objects together, nothing more. But Albert Einstein showed, beginning in 1915 with his general theory of relativity, that this intuitive picture is fundamentally wrong. Space and time are not separate entities, but form a unified four-dimensional fabric called spacetime. And this fabric is not rigid but flexible, capable of being curved and warped by the presence of mass and energy. Think of spacetime as a stretched rubber sheet. Place a bowling ball in the center and it creates a depression, a curve in the sheet. Smaller objects like marbles placed nearby will roll toward the bowling ball, not because of some mysterious force acting at a distance, but simply because they're following the curves in the sheet, taking the path of least resistance through the bent geometry. This is gravity in general relativity. Massive objects curve spacetime around them, and other objects moving through this curved spacetime follow trajectories that we interpret as being influenced by gravitational attraction. Near ordinary objects like Earth or the Sun, the curvature of spacetime is gentle. The effects of general relativity are subtle, producing tiny corrections to the predictions of Newton's classical theory of gravity. These corrections are measurable with precise instruments. They've been confirmed thousands of times in experiments and observations, but they don't dramatically change our everyday experience. However, near extremely dense objects, space-time curvature becomes dramatic. And at a black hole, space-time curvature becomes so extreme that it creates a region from which nothing, not even light itself, can escape. A black hole forms when matter becomes compressed to such extraordinary density that the escape velocity from its surface exceeds the speed of light. Escape velocity is the speed an object needs to break free from a gravitational pull. From Earth's surface, a rocket must reach about 25,000 miles per hour, or 11 kilometers per second, to escape into space. From the Sun's surface, the escape velocity is much higher, about 380,000 miles per hour, or 618 kilometers per second. But from the surface of a black hole's event horizon, the escape velocity exceeds 186,000 miles per second, the speed of light itself. Since nothing can travel faster than light, this represents an absolute physical limit built into the laws of nature. Nothing can escape from inside a black hole's event horizon. Photons of light emitted inward, or even parallel to the horizon, fall back toward the center. The event horizon is therefore an absolute boundary between the observable universe and the interior of the black hole. Information, matter, energy, anything that crosses the horizon is lost to the outside universe forever, though this absolute statement is complicated by quantum effects Stephen Hawking discovered decades later. Black holes come in different varieties, formed through different processes. Stellar mass black holes, those formed from collapsed stars, typically contain between 3 and a few dozen times the mass of the Sun. They form when massive stars, those with more than about 20 times the Sun's mass, exhaust their nuclear fuel. Throughout a star's life, it's supported against gravitational collapse by the outward pressure generated by nuclear fusion in its core. When the fuel runs out, this support disappears and the core implodes catastrophically, collapsing in a fraction of a second. If the core is massive enough, no known force can halt this collapse, and it continues until all the mass is concentrated in an infinitesimally small point called a singularity, surrounded by an event horizon. The formation of supermassive black holes remains one of the great puzzles in astrophysics. Unlike stellar mass black holes, which form from the collapse of individual stars through well-understood processes, supermassive black holes cannot possibly form this way. No star has ever existed or could ever exist with millions or billions of solar masses. The radiation pressure from nuclear fusion in such a massive star's core would blow it apart long before it could collapse. These behemoths must grow through other mechanisms, accumulating mass over time. But how they grow so large, and how they grow so large so quickly in the early universe, remains hotly debated. Several formation scenarios exist, each with strengths and weaknesses. Perhaps supermassive black holes grew from smaller seed black holes, the remnants of the first generation of stars in the early universe. These seeds might have been a few hundred to a few thousand solar masses initially, formed when the very first massive stars, made purely of hydrogen and helium with no heavier elements, collapsed shortly after the Big Bang. Over billions of years, they could grow by accreting gas from their surroundings and merging with other black holes when galaxies collide. Through this gradual process, a seed black hole might eventually reach millions or billions of solar masses. However, calculations show that this process faces significant challenges, especially for the most massive supermassive black holes, like phoenixa. Accreting matter isn't straightforward because as material falls toward a black hole, it heats up and emits intense radiation. This radiation exerts outward pressure on surrounding gas, potentially halting further accretion. There's a theoretical limit, called the Eddington limit, named after British astrophysicist Arthur Eddington, that describes the maximum rate at which a black hole can grow through accretion before the radiation pressure from the infalling material becomes strong enough to blow away any additional matter trying to fall in. For a black hole growing at the Eddington limit, starting from a seed mass of perhaps 100 solar masses formed from the first generation of stars, it would take several billion years to reach a billion solar masses. This seems fine for black holes in the nearby, and therefore more recent, universe. But astronomers have discovered supermassive black holes with billions of solar masses existing when the universe was less than 1 billion years old, just 7% of its current age. These black holes appear to have formed and grown to enormous sizes far too quickly for standard accretion models to explain. It's like finding a full-grown oak tree in a forest that was planted just last month. The timeline simply doesn't work under normal circumstances. This has led to alternative proposals. Perhaps in the dense, chaotic conditions of the early universe, massive gas clouds collapsed directly into black holes without ever forming stars. These direct collapse black holes could start with initial masses of thousands or even tens of thousands of solar masses, giving them a head start on growth. Starting from a much more massive seed, they could more easily reach billions of solar masses within the time available in the early universe. The conditions for direct collapse require preventing star formation while allowing the gas cloud to remain hot enough to avoid fragmenting, a delicate balance that may have been possible in primordial gas clouds. Or perhaps supermassive black holes grow faster than the Eddington limit under certain conditions. If the accretion disk around a young black hole is particularly thick and opaque, the radiation might be trapped and unable to escape efficiently. allowing matter to fall in faster than the Eddington limit would normally permit. Computer simulations of thick accretion disks show that under the right conditions, black holes can accrete at rates several times the Eddington limit for extended periods, dramatically speeding up their growth. This super-Eddington accretion might have been common in the early universe when gas supplies were plentiful and galaxy mergers frequent, providing a steady stream of fresh material. Phoenix A, with its 10 billion solar mass black hole, pushes these formation questions to their limits. This black hole is exceptionally massive, requiring highly efficient growth mechanisms operating over billions of years. It likely started from an unusually massive seed, perhaps 10,000 to 100,000 solar masses or more, placing it among the most massive seeds possible in theoretical models. It grew through exceptionally efficient accretion for billions of years, possibly exceeding the Eddington limit through super-Eddington accretion in its early history when the universe was denser and gas more abundant. And it underwent multiple major merger events when its host galaxy collided with other massive galaxies, each time absorbing another supermassive black hole and adding that mass to its own, while also triggering new episodes of gas accretion. The sheer improbability of all these factors aligning makes Phoenix A extraordinarily rare. The universe contains countless supermassive black holes numbering in the hundreds of billions, but only a handful approach or exceed 10 billion solar masses. These ultramassive black holes represent the absolute upper limit of what black hole formation processes can produce. The end result of every growth mechanism working at maximum efficiency for billions of years in the most favorable environments. Phoenix A may well be among the most massive black holes that will ever exist in the entire history of our universe. Understanding what Phoenix A looks like requires understanding the environment immediately surrounding it. The black hole itself, the event horizon, emits no light and is invisible by definition. But the region around it is anything but dark. This black hole sits at the center of an active galaxy, consuming enormous quantities of matter, and this feeding process creates one of the most luminous and energetic displays in the universe. Material doesn't fall straight into a black hole. Almost everything that approaches has some sideways motion, some angular momentum that causes it to swing past the black hole rather than plunging directly in. Conservation of angular momentum is a fundamental law of physics, like conservation of energy. As this material falls inward, conservation of angular momentum causes it to spiral around the black hole, gradually descending in a death spiral that can last thousands or millions of years depending on where the material starts. The result is an accretion disk, a swirling vortex of matter orbiting the black hole, looking somewhat like a cosmic hurricane with the black hole as its eye. For an ultramassive black hole like Phoenix A, this accretion disk is truly colossal in scale. The event horizon itself has a diameter of approximately 59 billion miles, or about 95 billion kilometers, roughly 630 times the distance from Earth to the Sun. To comprehend this scale, imagine that you could travel at the speed of light, the fastest possible speed in the universe. It would take you about 88 hours, nearly 4 days, to travel from one side of Phoenix A's event horizon to the other. The accretion disk extends far beyond this, potentially thousands or even tens of thousands of times farther, reaching out for light years from the center and containing more mass than millions of stars. As material in the accretion disk spirals inward, it speeds up and compresses, like a figure skater pulling in their arms to spin faster. This generates tremendous friction as faster-moving inner material rubs against slower-moving outer material, converting orbital kinetic energy into heat. This friction heats the disk to extreme temperatures. In the innermost regions, just outside the event horizon, temperatures can reach billions of degrees Kelvin, far hotter than the core of any star. Even the Sun's core, where nuclear fusion occurs, reaches only 15 million degrees. At these temperatures, matter doesn't behave like ordinary gas. Atoms are completely ionized, torn apart into free electrons and nuclei, forming what physicists call a plasma. This superheated plasma emits radiation across the entire electromagnetic spectrum, from low-energy radio waves through visible light to high-energy X-rays and gamma rays. The total luminosity, the total energy output per second from Phoenix A, is almost incomprehensible. Current estimates suggest it may be outputting energy at a rate exceeding 10 to the power of 40 watts or 100 billion trillion watts. To put this in perspective, our Sun outputs about 4 times 10 to the power of 26 watts. Phoenix A's accretion disk and jets are roughly 25 trillion times more luminous than the Sun. This single object, concentrated in a region smaller than a typical galaxy, outshines hundreds of billions of stars combined. The light from Phoenix A has been traveling through space for billions of years to reach us, and yet it still appears as a detectable point of light in our most powerful telescopes. This extraordinary luminosity has profound consequences for the surrounding environment. For millions of light years in all directions, the intense radiation from Phoenix A dominates the radiation environment. Any gas within this region is ionized by the onslaught of high-energy photons, stripped of electrons, and heated to temperatures of millions of degrees. Star formation becomes nearly impossible within this zone because gas clouds can't cool down and collapse under their own gravity. They're kept hot and puffed up by the relentless radiation bath, a process astronomers call AGN feedback. The radiation doesn't just heat gas, it pushes it. Photons carry momentum, and when they're absorbed or scattered by matter, they transfer this momentum, exerting pressure. For ultramassive black holes like Phoenix A, radiation pressure can launch powerful winds that blow gas away from the central region at speeds of thousands or even tens of thousands of miles per second. These winds can contain as much mass as millions of suns, all moving at a significant fraction of the speed of light, carrying away enormous amounts of energy and momentum. Observations from the James Webb Space Telescope in 2025 have revealed complex structures in these outflowing winds, showing filaments and shells of gas being pushed outward by the radiation and magnetic fields. Magnetic fields play an absolutely crucial role in the accretion process around Phoenix A. The plasma falling toward the black hole is ionized, meaning it consists of electrically charged particles, electrons and ions, and therefore threaded with magnetic field lines. These fields are generated and amplified within the disk itself through what's called a dynamo process, similar to the dynamo that generates Earth's magnetic field, but operating on vastly larger scales and with far more powerful results. But the most spectacular feature of Phoenix A isn't the accretion disk itself, it's the jets. Phoenix A produces two of the most powerful relativistic jets ever observed in the universe. These jets are narrow beams of matter and energy that stream away from the black hole's poles at speeds approaching 99% of the speed of light. They extend for millions of light years into space, far beyond the host galaxy, punching through the intergalactic medium and creating enormous lobes of radio, emitting plasma visible in radio telescopes across the world. The jets from Phoenix A are truly mind-boggling in scale. They extend for approximately 7.5 million light-years from end to end, making the entire jet system one of the largest single structures associated with any object in the observable universe. To put this in perspective, the entire Milky Way galaxy is about 100,000 light-years across. The jets from Phoenix A are 75 times longer than our entire galaxy. If you could somehow observe the Milky Way from the distance of Phoenix A, our entire galaxy, containing 200 to 400 billion stars, would appear smaller than the width of these jets. The formation of jets like those from Phoenix A requires two key ingredients working together: a rapidly spinning black hole and a strong, organized magnetic field threading through the accretion disk and extending out to the poles. The spin of the black hole twists space-time around it, a phenomenon called frame dragging, literally dragging space itself into rotation like honey swirling around a spoon. This was predicted by Einstein's equations and confirmed by observations of satellites orbiting Earth, though on much smaller scales. The energy powering these jets comes ultimately from two sources working in tandem. First, the rotational energy of the black hole itself, extracted through the twisting of magnetic field lines in the ergosphere, the region just outside the event horizon where space-time is dragged around with the black hole. This process, called the Blandford-Znajek mechanism after the physicists who proposed it, can extract significant rotational energy from spinning black holes. Second, the gravitational potential energy of material falling toward the black hole, which is converted into kinetic energy and magnetic field energy as matter spirals inward and crosses the event horizon. As matter spirals inward through the disk, a fraction of its mass energy is converted into the kinetic energy of jet particles and magnetic field energy in the jets, launching material outward at nearly the speed of light. For Phoenix A, the power output in the jets is estimated to exceed 10 to the power of 38 watts, or about 100 trillion times the energy output of our entire sun. This energy is concentrated in narrow beams, making them even more powerful per unit area. The jets carry this energy outward at nearly the speed of light, plowing into the surrounding intergalactic medium. When the jet material, moving at 99% light speed, slams into the relatively stationary intergalactic gas, it creates powerful shocks that heat the gas to temperatures of millions of degrees and accelerate particles to extreme energies approaching cosmic ray energies. These shocks form the brilliant radio lobes that extend millions of light-years on either side of Phoenix A. The lobes glow brightly at radio wavelengths because they're filled with high-energy electrons spiraling around magnetic field lines, producing what's called synchrotron radiation. This is the same mechanism that produces light in particle accelerators on Earth, but operating on cosmic scales. Radio observations reveal complex structure within these lobes, including filaments, knots, and hotspots where the jets directly impact the surrounding medium. The lobes represent a fossil record of millions of years of jet activity, preserved in the magnetized plasma that fills them. The jets don't just produce spectacular visual displays. They have profound physical effects on their surroundings that influence galaxy evolution across cosmic scales. As they plow through space, they push gas aside, creating enormous cavities in the intergalactic medium. These cavities can be hundreds of thousands or even millions of light-years across, regions where gas has been swept away or heated to such high temperatures that it emits primarily in X-rays rather than visible light. Radio observations combined with X-ray observations from satellites like Chandra and XMM Newton reveal these cavities clearly, dark voids in the X-ray emitting gas filled with radio emission from the jets. The energy deposited by the jets heats the surrounding gas on truly cosmic scales. Computer simulations of jet propagation show that as the jets push outward, they drive shocks into the ambient medium, heating gas across volumes encompassing millions of cubic light-years. This heating has important consequences for galaxy formation and evolution in the region. Hot gas cannot easily collapse to form new stars because it has too much thermal energy to overcome. The jets effectively suppress star formation across enormous regions of space, regulating galaxy growth. This is one of the primary mechanisms by which supermassive black holes influence galaxy evolution, a process astronomers call AGN feedback, where AGN stands for Active Galactic Nucleus. Phoenix A doesn't exist in isolation floating in empty space. It sits at the center of the Phoenix cluster, a massive collection of hundreds of galaxies bound together by gravity. Galaxy clusters are among the largest gravitationally bound structures in the universe, containing hundreds to thousands of galaxies, along with vast amounts of hot gas filling the space between galaxies. This intergalactic gas, though extremely low density by terrestrial standards, just one particle per cubic centimeter, compared to trillions of trillions per cubic centimeter in Earth's atmosphere, is far from empty. Given the enormous volumes involved, the total mass of this gas can exceed the mass of all the stars in all the galaxies combined. The Phoenix cluster is exceptional in several ways. First, it's one of the most massive galaxy clusters known, containing a total mass, including galaxies, gas, and dark matter, equivalent to about 2,000 trillion times the mass of our Sun. That's roughly 1,000 times the mass of the entire Milky Way galaxy. Second, the cluster shows evidence of exceptionally high rates of star formation in its central galaxy, the one hosting Phoenix A. Most massive elliptical galaxies at the centers of clusters are essentially dead, having exhausted their gas supplies billions of years ago and stopped forming stars. But Phoenix A's host galaxy is forming new stars at a rate of several hundred solar masses per year, extremely high for a galaxy of this type and age. This unusual star formation appears to be connected to the black hole's activity in complex ways that astronomers are still working to understand. While the jets from Phoenix A heat gas and suppress star formation on large scales across millions of light-years, on smaller scales near the center, the jets create complex flows and turbulence that can actually enhance star formation. Gas compressed by shock waves from the jets can become dense enough to overcome the heating and collapse to form stars, creating a complicated feedback loop where the black hole simultaneously suppresses and promotes star formation in different regions. Recent observations from JWST in 2025 have revealed filaments of cold, dense gas embedded within the hot cluster gas, cooling through emission of specific spectral lines and feeding both the black hole and star formation. This delicate balance between heating and cooling, between destruction and creation, plays out across the cluster and helps determine the evolution of the entire system. The relationship between Phoenix A and its host galaxy exemplifies one of the most important discoveries in modern astrophysics, the tight correlation between supermassive black hole mass and galaxy properties. Astronomers have found that the mass of a galaxy's central black hole correlates remarkably well with the mass of stars in the galaxy's central bulge and with the velocity dispersion of stars in the bulge, a measure of how fast stars are moving randomly. More massive galaxies have more massive black holes, with a ratio of black hole mass to bulge mass of approximately 1 to 1,000. The leading explanation for this correlation involves AGN feedback. As a galaxy grows and accumulates gas through mergers and accretion from cosmic filaments, its central black hole grows as well, fed by the same gas supply falling toward the center. When the black hole becomes sufficiently massive and begins feeding vigorously, its jets and radiation heat surrounding gas, driving powerful winds that can expel gas from the galaxy or prevent it from cooling and forming stars. This feedback limits both the galaxy's growth and the black hole's growth simultaneously, naturally producing a correlation between their final masses. The black hole essentially regulates its own growth by destroying its food supply. Phoenix A, with 10 billion solar masses, sits in a galaxy with a stellar mass estimated at several trillion solar masses, maintaining the expected ratio of approximately 1 to 1,000 between black hole mass and galactic bulge mass. The black hole and galaxy have co-evolved over billions of years, growing together through a complex interplay of gas accretion, star formation, galaxy mergers, and feedback processes. Understanding this co-evolution is crucial for understanding how galaxies like the Milky Way and ultimately solar systems like ours came to exist. The story of Phoenix A is, in a very real sense, part of our own story, part of the chain of cosmic events that led to the formation of our solar system and the emergence of life on Earth. The distance to Phoenix A is approximately 5.7 billion light-years, meaning the light we observe today left Phoenix A 5.7 billion years ago when the universe was about 8 billion years old, roughly 60% of its current age. At that time, Earth was already ancient, having formed 4.5 billion years earlier, and life had existed on our planet for over 3 billion years. At that cosmic epoch, the universe was smaller, denser, and hotter than today. The cosmic microwave background, the afterglow of the Big Bang that fills all of space, had a temperature about 1.6 times higher than today's 2.7 Kelvin. Galaxies were undergoing more frequent mergers because they were packed more closely together in space due to the universe's smaller size. Gas supplies were more abundant because less of the universe's hydrogen and helium had been locked up in stars and stellar remnants. And black holes were feeding more voraciously on average, producing the brilliant quasars that dominated the high-energy sky in that distant epoch. Phoenix A, as we observe it, represents a snapshot of a more active, more violent, more energetic era in cosmic history, a time when the universe was still young and vigorous. Measuring such vast distances requires sophisticated techniques developed over decades of astronomical research. Astronomers use the redshift of spectral lines, the stretching of light wavelengths caused by the expansion of the universe. This expansion, discovered by Edwin Hubble in 1929 through observations of distant galaxies, means that space itself is stretching, carrying galaxies apart like raisins in rising bread dough. As space expands, light waves traveling through it get stretched as well, shifting toward longer, redder wavelengths. The amount of stretching depends on how much the universe has expanded during the light's journey, which depends on the expansion rate and the distance. Phoenix A has a redshift of approximately 0.57, meaning wavelengths have been stretched by a factor of 1.57 since the light was emitted. A photon that left Phoenix A as blue light with a wavelength of 400 nanometers has been stretched during its journey across expanding space and arrives at Earth as orange light with a wavelength of 628 nanometers. At such distances, Phoenix A appears extremely faint in visible light despite its tremendous intrinsic luminosity. Its apparent magnitude is roughly 17 to 18, far too faint to see with a naked eye or even with binoculars. The human eye can see stars down to about magnitude 6 under perfect dark sky conditions. Phoenix A is roughly 40,000 times fainter than that limit. You would need at least an 8-inch telescope under dark skies to detect it at all, and even then, it would appear as nothing more than a faint smudge, indistinguishable from countless other distant galaxies scattered across the sky. To the naked eye, looking in the direction of Phoenix A in the southern constellation Phoenix, you would see nothing but empty blackness, perhaps a few foreground stars from our own galaxy, but no hint of the cosmic monster lurking beyond. But in radio wavelengths, Phoenix A is among the brightest sources in the southern sky, easily detectable with even modest radio telescopes and revealing the spectacular jet structure that makes this system so extraordinary. Radio astronomy operates at wavelengths thousands to millions of times longer than visible light, from millimeters to meters. At these wavelengths, the universe looks completely different from what we see with optical telescopes. Optical quasars may appear faint or invisible, while radio galaxies blaze brilliantly. Dust clouds that block visible light become transparent, allowing radio telescopes to peer into regions optical telescopes can never see. And the synchrotron emission from relativistic electrons spiraling in magnetic fields, the dominant emission mechanism in jets and radio lobes, shines brightly at these wavelengths. The radio observations of Phoenix A required state-of-the-art telescopes and techniques developed over decades. The Very Large Array in New Mexico, consisting of 27 radio dishes, each 25 meters in diameter, arranged in a Y-shaped configuration spanning up to 22 miles, provided high-resolution images of the jet structure with resolution approaching 1 arcsecond. The Australia Telescope Compact Array contributed observations from the southern hemisphere, where Phoenix A is better positioned in the sky, reaching higher elevations for longer observation periods. Space-based X-ray telescopes like Chandra and XMM Newton revealed the hot gas in the Phoenix cluster and the cavities carved by the jets, showing temperatures of tens of millions of degrees. And optical telescopes, including Hubble, studied the central galaxy and attempted to resolve the nuclear region where the black hole resides, measuring stellar velocities and gas motions. Combining observations across wavelengths creates a multi-messenger picture of Phoenix A, far richer than any single wavelength could provide. Radio observations show the jets and lobes extending millions of light-years, revealing the overall structure and energy content. X-ray observations reveal how the jets interact with the surrounding hot gas, creating shocks and cavities and depositing energy. Optical and infrared observations study the central galaxy, its stellar populations, and signs of ongoing star formation. Ultraviolet observations probe the accretion disk directly, seeing the hottest gas closest to the event horizon emitting at temperatures of hundreds of thousands of degrees. Each wavelength adds another layer to our understanding, like assembling a jigsaw puzzle where each piece comes from a different source, and only by combining all the pieces do we see the complete picture. The study of Phoenix A and similar ultramassive black holes has profound implications for our understanding of structure formation in the universe. Cosmologists have developed a hierarchical model of structure formation in which small structures form first and gradually merge to build larger structures over cosmic time. In the very early universe, less than 1 million years after the Big Bang, matter was distributed almost perfectly uniformly, with only tiny density variations of about 1 part in 100,000. These tiny variations, imprinted during cosmic inflation in the first fraction of a second after the Big Bang, were the seeds from which all cosmic structure would eventually grow through gravitational amplification. This hierarchical model successfully explains many observed properties of galaxies and large-scale structure. The cosmic web, that vast network of filaments and voids that defines large-scale structure on scales of hundreds of millions of light-years, emerges naturally from gravitational collapse of these initial density fluctuations. Computer simulations following billions of dark matter particles through cosmic time reproduce the observed distribution of galaxies with remarkable accuracy, matching everything from galaxy clustering on large scales to the internal structure of dark matter halos around individual galaxies. The model predicts that massive galaxies like Phoenix A's host should be rare, forming preferentially at the intersections of multiple filaments where matter naturally accumulates from multiple directions. And indeed, when we look at the universe on the largest scales, we find massive galaxy clusters like the Phoenix cluster located exactly where the simulations predict they should be at the nodes of the cosmic web. But ultramassive black holes like Phoenix A push this model in interesting ways and reveal gaps in our understanding. Growing a 10 billion solar mass black hole, while not impossible in the hierarchical framework, still requires exceptional efficiency at every stage of the process. The seed black hole must be substantial, likely at least several thousand solar masses, placing it at the high end of possible seed masses from the first generation of stars. The accretion must be vigorous and sustained over billions of years, requiring a steady supply of cold gas that can cool efficiently and fall toward the center without being dispersed by feedback. And the merger history must be rich, with multiple major mergers delivering additional black hole mass while also funneling gas toward the center to fuel accretion between mergers. What the simulations reveal is that black holes like Phoenix A represent the fortunate few, the winners of a cosmic lottery where everything aligned favorably. Most galaxies, even most massive galaxies, have smaller black holes. A typical massive elliptical galaxy might have a central black hole of 1 to 5 billion solar masses. Phoenix A, with 10 billion solar masses, represents the tail end of the distribution, the rare cases where growth efficiency was maximized. This tells us something important. Black hole growth is not automatically efficient. There are bottlenecks, limitations, feedback processes that normally prevent black holes from growing to extreme masses. Phoenix A somehow overcame or avoided these limitations, perhaps through an unusually massive seed, perhaps through particularly efficient accretion in its early history, or perhaps through an exceptional merger history. The existence of Phoenix A also constrains theoretical models of black hole formation and growth in subtle but important ways. Any successful theory must be able to explain not just typical supermassive black holes, but also the rare monsters at the extreme end of the mass distribution, like phoenix A. The theory must explain why such massive black holes exist at all, why they're rare but not impossibly rare, occurring perhaps once per several cubic billion light-years of space, and why they seem to be associated with massive galaxy clusters rather than being randomly distributed. These constraints help astronomers rule out models that can't produce ultramassive black holes or that predict they should be more common than observed. One possibility gaining attention is that the first black hole seeds in the early universe were more massive and more diverse than previously thought. Traditional models assumed that the first black holes formed from the first generation of massive stars called population 3 stars, which would produce stellar mass black holes of perhaps 10 to 100 solar masses. But if some regions experience direct collapse, where gas clouds collapse directly into black holes without forming stars first, the initial seeds could be much larger, perhaps 10,000 to 100,000 solar masses or even larger. These superseeds would have a tremendous head start on growth and could more easily reach 10 billion solar masses within the age of the universe, even with modest accretion rates. Alternatively, black holes might grow through super-Eddington accretion more commonly than standard models assume. The Eddington limit, named after British astrophysicist Arthur Eddington, who derived it in the 1920s, represents the maximum luminosity a spherically symmetric object can sustain while still accreting matter. Above this limit, radiation pressure becomes strong enough to blow away inflowing material, halting further accretion. For a 10 billion solar mass black hole, the Eddington luminosity is about 2.5 times 10 to the power of 40 watts. Phoenix A appears to be radiating at or somewhat below this level, suggesting it's accreting at a moderate rate consistent with the Eddington limit. Or perhaps major galaxy mergers, which deliver large gas supplies and merge central black holes, were more frequent in Phoenix A's history than current models predict, particularly in the overdense regions that would become massive galaxy clusters. Galaxy clusters are special environments, the largest gravitationally bound structures in the universe, containing thousands of trillions of solar masses. Within clusters, galaxies are packed more densely than in the general field, increasing the probability of close encounters and mergers by factors of 10 to 100. The central galaxy in a cluster, called the brightest cluster galaxy, or BCG, grows primarily through mergers with smaller galaxies that sink to the center through dynamical friction, a process where the galaxy loses orbital energy through gravitational interactions with surrounding matter. Phoenix A's host galaxy is precisely such a BCG, suggesting it has undergone many mergers over cosmic time, perhaps dozens of major mergers, each delivering billions of solar masses of stars and gas. Phoenix A will likely remain active for at least several million more years, continuing to consume gas from its surroundings and launch jets into the Phoenix cluster. The current accretion rate, estimated at 5 to 10 solar masses per year based on the observed luminosity and applying standard accretion efficiency models, can be sustained as long as cold gas continues to reach the central regions. The Phoenix cluster is unusual in showing high rates of star formation in its central galaxy, hundreds of solar masses per year, far higher than typical for brightest cluster galaxies, which usually form fewer than 1 solar mass per year. This suggests cold gas is somehow able to cool and collapse, despite the intense heating from Phoenix A's jets, perhaps in filaments or dense clouds that are able to resist disruption by the powerful outflows, falling toward the center along preferred directions. Eventually, over timescales of 10 to 100 million years, the gas supply will inevitably dwindle through various processes operating simultaneously. Star formation will consume some of the available gas, locking it up in long-lived stars that will shine for billions or trillions of years. The jets and radiation from Phoenix A will heat and disperse other gas, driving it out of the central region or heating it to such high temperatures that it can't cool and collapse on reasonable timescales without external compression. And some gas will be consumed by the black hole itself, disappearing forever beyond the event horizon and adding to Phoenix A's already immense mass. As the accretion rate declines, Phoenix A will dim gradually. The brilliant quasar we observe today will fade to a faint shadow of its former self over millions of years. The jets will weaken and eventually shut off entirely as insufficient power becomes available to drive them, leaving behind the fossil radio lobes as evidence of past activity. Phoenix A will enter a quiescent phase, a period of dormancy lasting potentially hundreds of millions or billions of years. In the far future, billions of years from now, Phoenix A will likely experience major mergers with other massive black holes as its host galaxy collides and merges with other large galaxies in the Phoenix cluster. Galaxy clusters are not static structures, but continue evolving over time, though more slowly than individual galaxies. While individual galaxies orbit within the cluster at speeds of hundreds or thousands of kilometers per second, the cluster as a whole may merge with other clusters over timescales of billions of years, creating even larger structures called superclusters. And within the cluster, the central galaxy continues growing through cannibalism, consuming smaller galaxies that wander too close and are torn apart by tidal forces. Eventually, the black holes come close enough, within a few light years or even light months, that gravitational radiation, the emission of gravitational waves, becomes the dominant energy loss mechanism. Gravitational waves are ripples in spacetime itself. Predicted by Einstein in 1916 as a consequence of general relativity and first directly detected by the LIGO Observatory in 2015 from merging stellar mass black holes. Just as accelerating electric charges produce electromagnetic waves rippling through electric and magnetic fields, accelerating masses produce gravitational waves rippling through the fabric of space-time itself. For most situations, gravitational wave emission is extraordinarily weak, far too weak to detect or to have any practical effect. But for massive objects moving at high velocities in strong gravitational fields, particularly orbiting black holes in their final moments before merger, gravitational wave emission becomes powerful and detectable across cosmic distances. When two supermassive black holes orbit each other at close range within a few light months, they emit gravitational waves that carry away orbital energy at an increasing rate. This causes the orbit to shrink, bringing the black holes closer together. As they get closer, they orbit faster, emit stronger gravitational waves, lose energy faster, and spiral inward even more rapidly. This creates a runaway process culminating in the final plunge and merger over the course of hours to days. The entire late stage in spiral, from initial contact at close range through final merger, produces a characteristic chirp signal, a gravitational wave that sweeps upward in frequency and amplitude as the orbit shrinks, reaching peak amplitude at the moment of merger before ringing down as the merged black hole settles into its final configuration like a struck bell gradually quieting. For Phoenix A, merging with another black hole of comparable mass, say 5 to 10 billion solar masses, the peak gravitational wave strain, the fractional stretching of space itself, would be detectable across the entire observable universe by future space-based gravitational wave detectors designed specifically for these frequencies. The Laser Interferometer Space Antenna, or LISA, planned for launch in the mid-2030s, will be sensitive to supermassive black hole mergers throughout cosmic history, going back to the very early universe. LISA will consist of 3 spacecraft flying in a triangular formation, each separated by 2.5 million kilometers, about 6 times the Earth-Moon distance. Laser beams bouncing between the spacecraft measure tiny changes in the separation caused by passing gravitational waves, with sensitivities sufficient to detect space-time strains as small as 1 part in 10 to the power of 20, equivalent to measuring the width of a human hair across the diameter of the solar system. When a merger like Phoenix A with another massive black hole occurs, LISA or its successors will detect the signal months or even years before the final plunge, tracking the inspiral as the black holes gradually spiral together in their cosmic dance. The gravitational wave signal encodes information about the masses of the 2 black holes, their spins which can range from 0 to nearly the speed of light, the geometry of the orbit including its eccentricity, and even the distance to the system through the amplitude of the signal. By analyzing the signal in detail using sophisticated data analysis techniques involving matching the observed signal to theoretical templates, astronomers can measure these properties with remarkable precision, often better than electromagnetic observations can achieve. The gravitational waves essentially carry a complete blueprint of the merger, written in the language of warped spacetime and decoded through Einstein's equations. And by combining gravitational wave observations with traditional electromagnetic observations, watching for optical, X-ray, or radio emission from the merger in what astronomers call multi-messenger astronomy, scientists can study these events in unprecedented detail, using multiple messengers, light, and gravitational waves to build a complete picture. This approach has already proven successful with stellar mass black hole mergers detected by LIGO and Virgo, where combining gravitational wave data with gamma-ray and optical observations provided insights impossible from either messenger alone. For supermassive black hole mergers like Phoenix A, the electromagnetic counterpart might be a brilliant flare as disrupted accretion disks collide and reform, or changes in jet direction as the merged black hole begins spinning in a new orientation. The matter that falls into Phoenix A crosses a boundary from which no return is possible, not even in principle. As material in the accretion disk spirals inward, approaching the event horizon, it accelerates to a significant fraction of the speed of light driven by the intense gravity. The orbital velocity just outside the event horizon approaches 50% of light speed for a non-rotating black hole and can exceed 90% for a rapidly spinning black hole near the maximum possible spin. Phoenix A, given its formation through multiple mergers and sustained accretion which both tend to spin up black holes, almost certainly spins rapidly, perhaps near the maximum possible rate, where the event horizon rotates at nearly the speed of light and frame dragging effects are maximized. At such speeds, relativistic effects become dramatic and impossible to ignore. Time dilation causes time to pass more slowly for rapidly moving material as measured by a distant observer, an effect that increases without limit as velocity approaches light speed. This isn't some subtle effect requiring sensitive instruments to detect. It's a profound alteration of reality itself, a consequence of the fundamental structure of space-time. Material's relativistic mass increases according to Einstein's equations, approaching infinity as speed approaches light speed, though this is better understood as momentum increasing without limit. And light emitted by the material is strongly Doppler shifted, blue shifted ahead in the direction of motion, and red shifted behind by factors that can reach 10 or more. These effects create the complex asymmetric structure observed in images of black hole accretion disks, with one side appearing brighter than the other due to relativistic beaming, where radiation is concentrated in the direction of motion like a searchlight beam, and due to gravitational lensing which bends light around the black hole. From the perspective of someone hypothetically falling into Phoenix A, an impossible journey, but one that helps us understand the physics, the experience would be unlike anything possible elsewhere in nature. Initially, far from the event horizon at distances of light years, the fall would feel like simple weightlessness, floating in space with a definite sense of direction toward the black hole. But there would be an overwhelming sense of scale. Phoenix A's event horizon is so large, 59 billion miles across, that even from relatively close distances, it wouldn't appear as a small disk, but as an enormous wall of darkness stretching across the sky, dominating the field of view. Looking around, the infalling observer would see the stars behind them, away from the black hole, appearing normal at first, perhaps slightly reddened due to gravitational redshift as photons climb out of the gravitational well. But looking toward Phoenix A, they would see something extraordinary and alien. The black hole itself would appear as a vast circular region of perfect blackness, absorbing all light that falls on it and emitting none, blocking light from stars behind it. Around this shadow, they might see a bright ring, the photon sphere, where light from the accretion disk is bent around the black hole by its extreme gravity and can orbit multiple times before escaping or falling in. The disk itself would appear as a glowing maelstrom, distorted by gravitational lensing into complex shapes, with the far side of the disk visible above and below the black hole's shadow due to extreme light bending. There would be no physical barrier at the event horizon, no sensation of passing through anything, no warning that a cosmic point of no return has been crossed. The crossing would be locally unremarkable from the infalling perspective. But after crossing, escape would be impossible by any means. Inside the event horizon, all future-directed paths in spacetime point inward toward the singularity at the center. Moving outward becomes as impossible as traveling backward in time, not just difficult, but prohibited by the structure of spacetime itself. The infalling person could still see outward for a time, observing light that fell in slightly after them, but any signals they sent would fall inward faster than they do, unable to reach the outside universe. The journey from event horizon to singularity, even for Phoenix A with its vast size, would be measured in hours or days, at most calculated from the infalling observer's clock. As they fell, tidal forces would eventually grow, slowly at first, given the black hole's enormous size, but eventually becoming lethal as they approached the singularity. The person would be stretched vertically while being compressed horizontally in the process called spaghettification, named for the pasta-like shape objects assume. Eventually, molecular and then atomic bonds would break down entirely as tidal forces exceeded nuclear binding energies. The person would be reduced to a stream of elementary particles falling toward the singularity. What happens at the singularity, the very center where all infalling matter eventually arrives according to Einstein's equations, remains one of the deepest mysteries in physics. General relativity predicts that at the singularity, density becomes infinite, space-time curvature becomes infinite, and the known laws of physics break down completely. Mathematically, the equations produce infinities when evaluated at the singularity, a clear sign that the theory has been pushed beyond its domain of validity. This is clearly an unphysical prediction, a signal that something is missing from our understanding. Nature abhors infinities. Whenever they appear in physical theories, they usually indicate the theory is incomplete or being applied inappropriately beyond its realm of applicability. Most physicists believe that quantum effects, which general relativity ignores since it's a classical theory, must become important at extremely small scales and prevent the formation of a true singularity with infinite density. Quantum mechanics tells us there's a fundamental limit to how small and dense something can be before quantum uncertainties dominate and the very concepts of position and density become ill-defined. This limit is set by the Planck length, about 10 to the power of negative 35 meters, roughly 20 orders of magnitude smaller than an atomic nucleus, and the Planck density, roughly 10 to the power of 96 kilograms per cubic meter. These are unimaginably small and large numbers respectively, far beyond anything we can probe experimentally, even in principle with current or foreseeable technology. At these scales, quantum fluctuations in the geometry of spacetime itself become important, as significant as the average curvature. Space and time may become grainy or discrete, rather than the smooth continuum assumed by classical general relativity. The very concepts of space and time may break down entirely, replaced by something more fundamental that we don't yet understand. Instead of a singularity with infinite density, there might be some kind of quantum structure at the black hole's core supported against further collapse. Perhaps a region where matter is compressed to the Planck density, but no further, held in some exotic quantum state we don't yet understand and can't yet describe with current theories. Some theories propose that the singularity is replaced by a Planck star, an object supported against further collapse by quantum pressure arising from the uncertainty principle, similar to how electron degeneracy pressure supports white dwarfs and neutron degeneracy pressure supports neutron stars. Others suggest the singularity might be a connection to another region of space-time, a wormhole leading somewhere else in our universe, or even to another universe, though this remains highly speculative and faces severe theoretical challenges, including instability problems. Or perhaps our entire conception of what happens inside black holes is wrong, and the interior is nothing like what general relativity predicts, with information preserved in ways we don't understand. We simply don't know with any confidence. The interior of black holes remains hidden behind event horizons forever beyond our ability to observe directly. Understanding what truly happens requires a theory of quantum gravity that successfully unites general relativity and quantum mechanics, merging our understanding of gravity and spacetime with our understanding of the quantum world of particles and fields. Despite decades of effort by thousands of theoretical physicists working on approaches like string theory, which proposes that fundamental particles are actually tiny vibrating strings in 10 or 11 dimensions, loop quantum gravity, which suggests spacetime itself has a discrete structure at the smallest scales like a fabric woven from quantum threads, and many others, this remains an unsolved problem, perhaps the deepest challenge in fundamental physics. Black holes, and especially ultramassive ones like Phoenix A, represent natural laboratories where these quantum gravity effects should be important, even if we can never observe them directly due to the event horizon. The conditions near the singularity represent the most extreme physics in the universe, where the rules we know must give way to something new and more fundamental. The ultimate fate of Phoenix A lies in the unimaginably distant future, trillions upon trillions of years from now, when the universe has evolved almost beyond recognition. In 1974, Stephen Hawking made a remarkable discovery that would fundamentally change our understanding of black holes and hint at a deep connection between gravity, quantum mechanics, and thermodynamics. He showed that when you combine quantum mechanics with general relativity, carefully analyzing quantum field theory in curved spacetime, black holes aren't completely black. They emit radiation, now called Hawking radiation, through a subtle quantum process occurring just outside the event horizon where quantum effects meet extreme gravity. Virtual particle pairs, constantly popping in and out of existence everywhere in space due to quantum fluctuations allowed by Heisenberg's uncertainty principle, can be separated by the intense tidal forces near the horizon. One particle falls in, while the other escapes to infinity, carrying away a tiny amount of energy that ultimately comes from the black hole's mass, according to Einstein's mass-energy equivalence. To an outside observer at large distance, the black hole appears to be radiating thermal radiation with a characteristic temperature. This was one of the most profound discoveries in theoretical physics, connecting black holes to thermodynamics and suggesting that black holes have entropy proportional to their event horizon area. This radiation is extraordinarily faint for massive black holes like Phoenix A. The temperature of Hawking radiation is inversely proportional to the black hole's mass, calculated from a formula involving fundamental constants. For Phoenix A, with 10 billion solar masses, the temperature is about 6 10-billionths of a Kelvin, 6 times 10 to the power of -11 Kelvin, far colder than the cosmic microwave background radiation that currently fills the universe at 2.7 Kelvin. This means Phoenix A is actually absorbing more energy from the cosmic background than it emits through Hawking radiation by a factor of roughly 45 billion. It's growing, not shrinking, albeit extremely slowly, at just a few atoms per second from CMB absorption, essentially negligible compared to its mass. But the universe is expanding and cooling according to the laws of thermodynamics and cosmology. The cosmic microwave background temperature decreases inversely with the scale factor of the universe, so as the universe doubles in size, the temperature drops by half. In about 100 trillion years, 10 to the power of 14 years, roughly 7,000 times the current age of the universe, the last stars will exhaust their fuel and die. Low-mass red dwarfs, the longest-lived stars, will have burned through their hydrogen after trillions of years of slow fusion. The universe will enter what cosmologists call the degenerate era, dominated by stellar remnants like white dwarfs glowing dimly from residual heat, neutron stars spinning down gradually, and black holes of all masses. The cosmic microwave background will have cooled to a fraction of a Kelvin, still above absolute zero, but approaching it asymptotically. Eventually, perhaps around 10 to the power of 20 years in the future, when the universe is 1 billion times older than it is today, the background temperature will cool below the Hawking temperature of Phoenix A. At that point, Phoenix A will begin to evaporate very slowly, losing mass through Hawking radiation faster than it gains mass from absorbing the ultra-cold background radiation. The evaporation timescale for a black hole is proportional to the cube of its mass, calculated from Hawking's formulas. For Phoenix A with 10 billion solar masses, the time to completely evaporate is approximately 5 times 10 to the power of 98 years. That's a 5 followed by 98 zeros, a number so incomprehensibly large it has no meaningful analogy or comparison in human experience. For comparison, the current age of the universe is less than 10 to the power of 11 years. The evaporation time for Phoenix A is roughly 5 times 10 to the power of 87 times longer than the current age of the universe. During this time, the universe will have expanded to unimaginable size, with the distance between surviving black holes exceeding the size of our currently observable universe, cooled to temperatures barely distinguishable from absolute zero, and become unrecognizably different from the cosmos we see today. But eventually, given enough time and patience, even Phoenix A will evaporate completely through the relentless process of quantum emission. The final stages of evaporation would be dramatic if anyone were around to witness them, which of course they won't be, since life as we know it will have become impossible long before. As the black hole shrinks, its Hawking temperature increases inversely with mass, causing it to radiate faster and shrink even more rapidly in a runaway process. When the black hole reaches roughly the mass of a mountain, corresponding to a size smaller than an atomic nucleus, it radiates with the luminosity of a star. In its final microseconds, it radiates with the power of billions of suns. The final moments would produce a burst of high-energy radiation, particles and photons of all types, as the last remnants of mass energy are converted according to E equals mc squared. Then Phoenix A would be gone completely, its immense mass scattered across the universe as faint radiation that will eventually thermalize with the background, leaving behind nothing but the memory encoded in the structure of space-time itself, and perhaps in whatever quantum information theory ultimately tells us about black holes. This is the heat death, the final equilibrium state predicted by thermodynamics when applied to cosmology. The universe approaches maximum entropy, a state of complete thermal equilibrium where no energy gradients exist to power any processes, no stars shine, no black holes lurk. Only an ultra-cold bath of ultra-dilute radiation approaching absolute zero temperature exists, stretched across an ever-expanding universe approaching infinite size. Time effectively becomes meaningless when nothing changes. This represents the ultimate fate of everything, including Phoenix A. But this lies so far in the future that for practical purposes, it might as well be infinity. But that lies unimaginably far in the future beyond human comprehension. For now, in our current epoch, just under 14 billion years after the Big Bang, Phoenix A exists in its terrible glory. A black hole 10 billion times more massive than our Sun. An object so extreme it challenges our ability to explain its formation. A gravitational monster that shapes its host galaxy and influences cosmic evolution on the largest scales. The jets extending 7.5 million light-years make it among the largest single structures associated with any object in the universe, dwarfing entire galaxy clusters. And its existence at the center of a massive galaxy cluster makes it a laboratory for studying the interplay between black holes and their environments, how supermassive black holes influence and are influenced by their cosmic surroundings. The discovery and study of Phoenix A represents human curiosity and ingenuity at its finest. Using nothing but clever observations, mathematical reasoning, and dedicated effort spanning decades, astronomers have measured and characterized an object nearly 6 billion light-years away, so distant, its light has been traveling toward us since before complex life diversified on Earth during the Cambrian explosion. They've determined its mass to within a factor of 2, understood the physics powering its jets through comparison with theory, mapped its influence on surrounding galaxies, and placed it in the context of cosmic evolution spanning the entire history of the universe. They've done this without visiting it, without touching it, using only the light it emits and the laws of physics we've discovered. This achievement required international cooperation involving scientists from dozens of countries, sophisticated technology pushing the boundaries of engineering, and theoretical frameworks developed over more than a century of physics research. It required Einstein's general relativity developed in 1915 to understand black holes fundamentally and predict their existence decades before observational confirmation. It required quantum mechanics developed in the 1920s to understand matter under extreme conditions and predict phenomena like Hawking radiation. It required decades of telescope development pushing radio, optical, and X-ray astronomy to their limits with ever larger mirrors and more sensitive detectors. And it required patient work by countless astronomers, many spending entire careers studying objects like Phoenix A, analyzing data, developing theories, and gradually building our understanding piece by piece. The universe contains more wonders than we have yet discovered, more objects pushing the limits of physics in ways we haven't imagined. Phoenix A, extraordinary as it is just one example of nature's extremes, one data point in understanding how matter and energy behave under the most extreme conditions. There may be even more massive black holes awaiting discovery in the distant universe, though Phoenix A likely sits near the absolute maximum mass possible given current theories. There may be exotic phenomena we haven't imagined occurring in extreme environments near these objects, perhaps involving quantum gravity effects or new physics beyond our current understanding. And countless questions remain about how these monsters form, how they evolve over cosmic time, and how they influence cosmic history. As our telescopes grow more powerful, we will continue probing these questions with ever greater precision and reaching ever more distant cosmic epochs. The James Webb Space Telescope, launched in 2021, is discovering quasars at unprecedented distances. Observing supermassive black holes as they existed less than 1 billion years after the Big Bang, when they shouldn't exist, according to our theories, yet somehow do. Future telescopes now being planned will image black holes with greater detail than ever before, perhaps capturing dynamics of matter spiraling into these cosmic drains in near real time. The next generation Event Horizon Telescope, with additional stations and improved technology, aims to create actual movies of matter-orbiting black holes instead of single images, watching material circle the event horizon before disappearing forever into the abyss. These observations will test general relativity with unprecedented precision in the most extreme gravitational fields nature produces, potentially revealing deviations that could point toward new physics and quantum gravity effects. The NGEHT, as it's called, will add new telescopes in Africa, South America, and on Greenland, increasing the array's coverage and resolution by factors of several. With these improvements, astronomers hope to measure the spins of supermassive black holes directly by observing how spacetime is dragged around them. A phenomenon called frame dragging that creates observable asymmetries in the emission patterns from the innermost accretion disk. Gravitational wave observatories are beginning to observe mergers of supermassive black holes, the process that likely contributed to building Phoenix A through multiple merger events. As these observatories become more sensitive with next-generation ground-based detectors and space-based observatories like LISA, they'll detect more distant and more massive mergers, eventually observing collisions of ultramassive black holes like Phoenix A itself when it merges with another giant in the far future billions of years from now. These observations will provide completely independent measurements of black hole masses and spins, testing our understanding of general relativity in the most extreme regime. The story of Phoenix A is far from complete. Each new observation adds another piece to the puzzle, another constraint on theories. Each theoretical advance deepens understanding and makes new predictions. And each discovery raises new questions, driving further investigation in an endless cycle. This is science's nature, an endless frontier where each answer reveals new questions, where knowledge grows, but so does awareness of how much remains unknown. The universe reveals itself gradually, reluctantly, only to those who ask carefully and listen patiently. 10 billion times the mass of our Sun, jets extending 7.5 million light-years, carrying the power of 100 trillion suns. A gravitational well so deep it bends space-time nearly to breaking and traps even light itself. This is Phoenix A. This is what nature can produce, given enough time measured in billions of years, enough matter measured in the masses of tens of billions of stars. And gravity's relentless pull operating according to Einstein's equations. And this is what human beings, tiny creatures on a tiny planet orbiting an ordinary star in an ordinary galaxy's outer suburbs, have managed to discover, measure, and begin to understand through centuries of accumulated knowledge. The universe is vast beyond imagination, containing hundreds of billions of galaxies, each with hundreds of billions of stars spread across billions of light-years of space and time. But we are part of this universe, made of the same matter, forged in stellar cores, governed by the same laws discovered through experiment and observation, connected to everything from the smallest quantum particles to the largest black holes by an unbroken chain of physical causation stretching back to the Big Bang 13.8 billion years ago. When we study Phoenix A, we're not studying something foreign or alien in a fundamental sense. We're studying our own cosmic origins, our own nature, the universe understanding itself through us as conscious observers. The monster at the heart of a distant galaxy cluster, shining across billions of light-years of space and time, has taught us profound lessons about reality. It has shown us gravity's power at its most extreme, bending space-time so severely that escape becomes impossible. It has revealed how galaxies and black holes grow together through cosmic history in a complex dance of matter and energy. It has tested our physics theories in conditions impossible to reproduce on Earth or in any laboratory, confirming Einstein's century-old predictions. And it has reminded us that no matter how much we learn, the universe always has more secrets to reveal, more wonders to discover, more questions to challenge our understanding and drive us forward. Phoenix A exists not as some distant abstraction or mathematical construct, but as a real physical object occupying space and time. A concentration of matter and energy obeying the same fundamental laws that govern everything from atoms to galaxies. It formed through processes we are beginning to understand involving the collapse of matter and the accretion of gas over billions of years, influences its surroundings in ways we can observe and measure through multiple wavelengths of light and eventually gravitational waves, and will continue evolving according to physics laws throughout our cosmos's unimaginable future until long after every star has died and even the black holes themselves evaporate. This black hole, 10 billion times more massive than the sun that gives us life, stands as testament to the extraordinary universe we inhabit and to the extraordinary capability of human beings to comprehend it through science. From our small planet, using instruments we have built and theories we have developed through centuries of accumulated effort, we reach across the cosmos to touch and understand objects that dwarf our entire world and exceed our everyday experience by factors of trillions. We are, quite literally, the universe becoming conscious of itself, matter, organized in such a way as to contemplate its own existence and origins. And in objects like Phoenix A, we see ourselves reflected on the grandest possible scale, reminded both of our cosmic insignificance and of our unique ability to comprehend the incomprehensible.